Welcome to the Hydrogen Fuel Cells Europe at this year's Hannovermesse 2022. My name is Muriel Burkas and we are here at a technical forum, also for everybody listening and watching remotely. A warm welcome to you. We are already on the last day of this year's Hannovermesse, so it's not just the last day, it's also the very last presentation here at the Technical Forum. So please join for the last presentation, have a seat, have some refreshments and enjoy this presentation. What will be the presentation about? International supply chains for a sustainable hydrogen economy in Germany. Please give a warm applause for the head of Group Power to Gas from the Fraunhofer ESE, Christopher Voglstätter.
Thank you for the nice introduction. As mentioned already, I would like to talk today a little bit about our activities concerning the analysis of international supply chains for a sustainable hydrogen economy in Germany. And I would of course like to start with a little bit introduction about our institute. So I'm representing today the Fraunhofer Institute for Solar Energy Systems. We are a renewable energy research institute with around 1,400 employees currently. And we have our research topics are centered around renewable energy research. That means we have a strong focus on photovoltaics and different kinds of photovoltaics and respective materials and further topics. But we also have a lot of activities concerning energy efficient buildings, solar thermal power plants and industrial processes, power electronics and grids and intelligent systems, and of course hydrogen technologies and electrical energy storage. I'm heading the group Power to Gas, and what we're doing is we're analyzing hydrogen plants and infrastructure. That means we're doing a lot of theoretical work, and we're using our models to do a techno-economical analysis of hydrogen plants and infrastructure. But we're not only analyzing, we're also doing concepts and technical optimizations of these plants. And we're not only doing that for single plants, but also for whole regions and supply chains. That means we're also doing geo-techno-economic analysis of isolated hydrogen regions, model regions, and of international supply chains. We also have a little bit of experimental work. That means we are operating the demonstration plants, the hydrogen demonstration plants of our institute. In specific, these are the hydrogen refueling stations since 2012 and our hydrogen injection station since 2017. And we use these to actually test components at our research platforms for use in the respective fields. We use our knowledge from these plants to also do technical monitoring and evaluation of hydrogen plants in the field or in field operation, and to condition-based maintenance for these kinds of plants. So we are talking today about hydrogen supply chains. Why are we actually talking about hydrogen supply chains? And the reason for that can be seen very clearly if we are looking at energy system analysis results. So what you can see here are results from an energy system analysis of the German energy system in the future, with the goal of having carbon neutrality in 2050. So this is before the targets have been decreased, or the timeline has been decreased. And you can already see that if you're looking at a future energy system, we have a certain demand of synthetic fuels in our energy system. In green, you can see the domestic production of synthetic fuels. Bright green is domestic hydrogen production, a little bit darker green is domestic syngas production, so methane production, and we have some fuels. And you can also see in blue that import is a relevant topic as well. That means additional to our domestic hydrogen production, we expect to have significant hydrogen imports as well. And these will start a little bit later, so 2030, only small amounts, but in the future, larger amounts of hydrogen import are expected. And you can see there are different bars with different height. That means the ratio or the amount of import is of course dependent on the price assumptions and on political decisions, and that makes a little bit of a difference. But you can also see in 2050, in a full renewable energy system, hydrogen imports do play, or we expect hydrogen imports to play a role. So if we're talking about supply chains, we need to talk about the different parts of the supply chain that are necessary to address and to analyze. So of course, we start on the left with renewable energy production. That means we have some kind of wind power plant, we have some kind of solar power plant, perhaps we have hydro or something else. And this supplies power to a water electrolysis in the top. And with water and the power from the renewable energy plants, we produce hydrogen. So if we're talking about international supply chains, we have to transport these kind of energy to Germany. That means either we feed it into a hydrogen pipeline, or we want to use liquid hydrogen from further remote areas. That means we need to liquefy it in a liquefaction unit, pump it into a bunker ship, and transport it to Germany. If we are looking at different kinds of synthesis product energy carrier, we also need a little bit of additional carbon dioxide, carbon monoxide, or nitrogen. That means we need to get carbon monoxide, carbon dioxide either from a co-electrolysis, from industry emissions or biogas plants, or from direct air capture. And we can use it together with hydrogen to produce methanol and put it into a ship and transport it, or use it in a refinery to produce different kinds of fuels. Or we can see it, and this is not clear, not very visible, we can do some upgrading and use methanol to actually produce chemicals. If we're looking at ammonia as a resource or energy carrier, we need nitrogen. That means we need an air separation unit. We feed that in an ammonia synthesis plant. We produce ammonia, and we can again put it in a bunker ship and transport it via the sea. So I would like to talk a bit about our approach to analyzing hydrogen supply chains. So first step in all our analysis is a GIS analysis of the countries in order to identify well-suited or best-suited regions for hydrogen or synthesis production plants. That means we take into account population density, renewable energies, and so on. Weather data in order to identify interesting regions. We use an internal database with a lot of different parameters for technological parts like the electrolysis plants today and in the future, efficiencies, capex, and so on. And we have to define a couple of boundary conditions, like, for example, the export destination. And with these kind of data, we generate the necessary time series for our simulation. That means we generate data, for example, for wind and solar production. We look at transport routes that are possible to use, for example, based on real-world shipping routes. And with that, we do a modeling and simulation. That means we put together all the different parts of the hydrogen production system or supply chain or synthesis production system in order to model the whole chain. We do that with a dynamic, non-linear modeling of this approach. That means we are able to actually see changes during the year. We can see different non-linear efficiency curves and stuff like that. We also can consider operation management decisions. For example, if you want to use part of the electricity provided for other purposes, for example, for local electricity supply to the region, or for something totally different, or we want to use some part of the hydrogen for local use, we can include that in our model and take then this whole model and simulate one typical year of this hydrogen supply chain and see then a lot of different results. But what we also usually do is we put an optimization algorithm to work in order to optimize the whole setup towards a typical criteria. So we are more or less free to actually optimize towards any parameter, but usually it always comes down to cost. So the typical parameter is hydrogen production costs, and that is usually what we optimize for. And with this, we get a couple of results. So this is on the one hand side, a set of key performance indicators, like, for example, the levelized costs of the hydrogen production quantity, so how many tons do we export, what's the investment cost, what's the system efficiency, what are the full-out hours, and so on. And we also get the plant design in the description of the plant design in the optimum, in the cost optimum. And this is what a typical result looks like. And now we have to look a little bit more into detail. So what you can see here is a comparison of different export routes and energy carriers for hydrogen or synthesis production in NEOM, so in the northwest of Saudi Arabia. We are not simulating pipelines here, but only ship transport. That means we have available liquid hydrogen, we have available ammonia, and we have available methanol. And you can also see we have different years printed below that, so with a cost decrease. The reason for that is that we also include cost decreases and cost digressions and efficiency increase via technological improvements. That means we take improvements into account for the year 2030 for renewables. We take improvements into account for the electrolysis plant, and with that we have a decrease in costs over the year. So, if we're looking at the different, or we can look into detail, perhaps at the in the left bar, so the 2020 liquid hydrogen bar. What you can see in the bottom, in green and yellow, are the electricity production costs. So around 70 euro per megawatt hour are the electricity production costs for the specific plants. If you want to produce hydrogen, we need an electrolysis system. That means we need the blue bar as well. And with that, we achieve around 100 euro per megawatt hour of hydrogen production in 2020. That is roughly 3 euros per kilogram. And the remaining stuff, except the little green bar at the top, are actually transport costs. That means for the liquefaction, we need a liquefaction unit. We need some kind of storage on site. We need a ship. And these are the costs that make up the 3 bars on top. And the little green is only a bit of engineering that comes on top of everything. You can also see that we have an arrow bar, which goes from around 140 to up to 230 euros per megawatt hour. That is the impact of the weighted average capital costs. That means, you can see there, we have the lower end of the bar is 2% weighted average capital costs, and the upper bar end is 10%. And that is the impact of this range. And this parameter is very different from each country that you build in, and depending on political boundary conditions that are set. So it is a very important parameter that has nothing to do with technology, but instead with a lot of political decisions and risk. So now it's time to compare the different energy carriers for this specific location. So what you have to keep in mind is that we address here only hydrogen or synthesis product generation and transport to the target harbor. That means if we are talking ammonia, we are talking about getting ammonia to Hamburg, but not about reconverting it to hydrogen. So it's using ammonia at the target harbor. The same is true for methanol, the same is true for liquid hydrogen. And it is important to say we didn't do any design optimization. So it's just putting together the different parts of the plant, running an optimization over it, so scaling the different components, but not doing anything that it might improve efficiency or reduce costs technologically. Waste heat usage, not a topic here. Needs a bit more detailed analysis. So if we're comparing that, you can see that liquid hydrogen and ammonia are very close in terms of cost. So there is a slight difference, but I'd say this is the precision of what we're actually doing here is less than the difference between the two carriers. But we can see that methanol is rather large. And the reason for that is that we have a direct air capture unit. So we didn't use a carbon dioxide source, like, for example, a power plant, coal power plant, or we didn't use anything like a biomass power plant or something like that. So we need to do direct air capture. And that is actually what is very expensive in the 2020 case. And has a slight decrease over the next years and makes methanol a bit more expensive. So we're talking about, producing of hydrogen in the desert. That means a lot of discussion always goes towards, in the desert there is no water, and if you use the water that's available there, that's not a good idea because you take water that is needed elsewhere. So what we have been doing in the last couple of months is that we included water supply into our models. That means we can now look at the different regions and see, is there enough water available for our electrolysis plant? And if not, what is the cost of desalinating seawater, transporting it to the specific location of the electrolysis plant, and of course, look, if you're looking a little bit more into detail, look at ways to actually improve the efficiency or the cost of that. For example, again, using waste heat that occurs anyway, and use it to actually reduce energy consumption of the desalination plant. And you can see on the right, for the northwestern African, part of this region, what the costs for desalinating and transporting water to the specific locations are, based or concentrated on or between in relation to the hydrogen production costs. That means we have previously heard we have around €3 per kilogram to actually produce hydrogen there, and then we have the cost of transporting it. 20% of that is the water desalination, if we are doing it in the red parts of this map. So this is about the hydrogen import via ships, but I'd like to do a very brief sneak preview at another import scenario. And this is a large-scale offshore wind hydrogen production plant in the sea. That is currently a project that is ongoing, so we don't have final results yet. It's just a sneak preview. And so what you see here is the schematic visualization of a plan, of a detailed plant feasibility study of a 500 megawatt offshore platform, and our role in that was to actually design the 10 megawatt electrolysis module and to again analyze the whole system and different transport routes to the next harbor. And with that, I'm finished, and I'd like to, if you have any questions that exceed this forum, feel free to find us at booth 39. I'll be there for the next hour and happy to discuss and answer all questions that you might have. Thank you very much.
Thank you very much, Christoph Voglstätter. He saw me standing there and kind of started rushing through. I'm so sorry. We have to make sure that we are keeping the time because of the live streaming mainly. So this was our very last presentation. So the time is up. So please go to the booth or ask him right here after he steps down from the stage any questions. It was very interesting. Thank you so much for being here.